In this video, I will give a simple explanation of Kirchhoff's loop rule and explain how to use it to set up equations for circuit analysis. Kirchhoff's loop rule, which is also known as Kirchhoff's second law, says the sum of all the voltage changes around any closed circuit loop must be zero. We will use this circuit shown on the screen to understand how to set up equations. But before we do, let's try to understand why this law makes sense by making an analogy with hiking. Imagine you are hiking a trail that starts and ends at the same point. Along the way, you go uphill and downhill and maybe uphill again, but by the time you return to the starting point, the sum of all the elevation changes must be zero because you are back at where you started. We can rephrase this idea as the sum of all the elevation changes around any closed hiking loop must be zero. Kirchhoff's loop rule is essentially based on the same idea. If I imagine going around a closed loop in a circuit, the sum of all the voltage changes, which is analogous to elevation changes, must be zero. Let's now discuss how to set up the loop rule mathematically. First, if the problem you are working on does not already specify the directions of the currents, assign a direction to each branch of the circuit. The choice of the direction is arbitrary. If the actual current flows in the opposite direction, it will result in a negative value for the current. In this circuit, there are three branches, one on the left, which goes through the battery with voltage E1 and resistor R1. I will call the current I1 and assume that it flows upward through the battery. The branch in the middle has resistor R2 and the battery with voltage E2. Let's assume that the current flows downward through this branch and call it I2. The branch on the right has battery with voltage E3 and resistor R3, and I will assume that the current flows upward through them and label it as I3. Next, we need to choose a closed loop. This loop can be any path that starts and ends at the same point, and it can go clockwise or counterclockwise. In this case, I will choose this large loop, starting from the top side of the battery on the left, and choose counterclockwise for the direction. Along this loop, there are two batteries and two resistors, so we expect to have four terms in our equation, one for each voltage change. The first circuit element we encounter is the battery on the left. In the circuit symbol for a battery, the long bar represents the positive terminal, while the short bar represents the negative terminal. In this case, the battery's positive terminal is on the top, and the negative terminal is on the bottom. As I move across the battery, I go from the positive side to the negative side, so the voltage change for this battery is negative, or negative E1. Next circuit element I encounter is resistor R1. As you probably learned before, Ohm's law tells us that the voltage difference across a resistor is I times R. There's no junction between the battery on the left and R1, making the current through R1 equal to I1. So the voltage difference across the resistor should be I1 times R1. The question is whether it should come with a positive sign or a negative sign. To determine this, it might be helpful to use an analogy with river flow. Water naturally flows from a higher elevation to a lower elevation. So if the river flows from right to left as it is shown in the schematic diagram, we know that the right side must be at a higher elevation than the left side. Similarly, since the current flows from right to left in resistor R1, we know that the right side must be at a higher voltage than the left side. So as I move across the resistor, I go from the low to high voltage, making the voltage change positive. And the voltage change for the resistor should be positive I1 R1. The next circuit element I encounter is resistor R3. This time, current I3 flows upward. Again, remembering that the current flows from high to low voltage, we can identify that the bottom side of the resistor should have a higher voltage. This implies that as I go across R3, the voltage decreases, making the voltage change negative I3 times R3. Lastly, it is the battery with voltage E3. This battery has its positive terminal facing up and the negative terminal facing down. Moving upward across the battery, I go from the negative side to the positive side, which is an increase. So we get positive E3 for the voltage change. Now that I am back where I started, I can say that the sum of all these voltage changes is equal to 0. So this is the equation I get for loop 1. Using the same approach, we can also find the equation for this loop 2. I am not going to go through it in details, but you should be able to show that we get this equation. Thank you for watching. In the next video, I will walk through a practice problem using Kirchhoff's loop rule and junction rule.